Okay, continuing where we left off, we've talked about finding the intervals where a function is increasing and decreasing, and it turns out it's a very small step to then determine where a function will have a local max, and of course we'll do a local min. So let's define a local max. I think we pretty much got the idea, but it's a point where f of x changes from increasing to decreasing. So it might do that in this smooth motion, like a nice curve, or it might do it rather abruptly with a cusp. In either case, as you move from left to right, the function is increasing and then decreasing, increasing, then decreasing. Okay. In the same way, we can define a local min, a point where the function changes from decreasing to increasing, and I only drew the smooth curve style. Of course, you could have one that has a cusp. I think you get the idea. So, how can we find these locations without even seeing the graph? Here's our first derivative test, is what it's referred to because it uses the first derivative. And what is it a test for? And it's not really clear in the name. It's for local extrema is the word that people use. Extrema, well, those are the extreme points, the local mins and the local maxes. So here's the test to find where your local mins and maxes occur. Number one, find the intervals of increasing and decreasing. So that itself is its own test with its own steps. But if once you find the intervals of increasing and decreasing, then there's really no work, very, very little work at all from there. Just looking at your domain line and seeing all your positives and negatives, identify the x values of local maxes and the x values of local mins. Once you identify them from your domain line, then it's just a matter of computing the y values for each of those and answering the question. So I went and I'm just gonna show you an example based on that first one that we did with increasing and decreasing. And like I said, there's very, very little work, if any, once you have the intervals of increasing and decreasing. So if you remember that first example we did, f of x equals negative x to the third plus 3x plus 5. We got to this domain line with these positives and negatives. The criticals were at -1 and +1, and it went negative, positive, negative. So we knew the interval of increasing was there in the middle, and the intervals of decreasing there on the sides. Okay, but what if it's not so much that we're interested in the intervals of increasing and decreasing? What if it's the local extrema that we care about? So we could say, hey, this first one, at -1, it changed from negative to positive. The function was decreasing, then it started increasing. That must be a local min. And at +1, the function was increasing and then decreasing. That must be a local max. And there's no work to do there. We can just see it. Now, we need the full point. All we know are the x values. So we're going to take each of those x values and plug them back into the original function so that we can know where those y values are. So we'll take the -1, plug it back into the original function right there, plug -1 in, and you will get 3. Take +1, same idea, you'll get 7. And so we know the local min is at -1, -1, comma 3. The local max was at +1. So we can say the full point now, +1, 7 is our local max. When it comes to these tests, and we're going to get another test, actually 2 more tests in the next section. You have to really keep in mind when you should plug values into which function, right? Here we plug these into the original function f. To get these positive and negatives, we plug numbers into the derivative. So just be very aware, when should I plug a number into the derivative? When should I plug a number into the original function? Because it's easy to mix that stuff up. Okay, let's do a full example of something new, a little bit harder. We have not done something quite like this. So our directions here are simply find the local extrema. Okay, we've got f of x equals x squared over x plus 1. So in our test for local extrema, first derivative test, first thing we need to do is find the intervals of increasing and decreasing. And well, to do that, of course, we need to find the criticals. And to find the criticals, we need to find the derivative. And there's lots of layers to these questions. They're not short. So hopefully by now, a function like this, its derivative, you feel pretty confident, right? We're going to use the quotient rule. So here I've got low d high minus high d low all over the low squared. Okay. Now I really want to simplify this. Turns out just the numerator cleans up. So if I distribute there with the parentheses, and then I combine my like terms, comes out pretty nice. Not too much going on here with this simplify. F prime of x equals x squared plus 2x over the quantity x plus 1 squared. Okay, really not spending a lot of time talking about the derivative because we've got quite a bit more to do. Hopefully you feel comfortable with that. Okay, so to continue with the criticals, there are two types of critical numbers. There's when the derivative equals 0, and there's when the derivative does not exist. So let's look at each of those, and let's just do this side by side. We can set the derivative equal to 0. To begin this one, to begin the does not exist, you notice I'm simply taking the denominator and setting it equal to 0. So it's kind of an equal to 0 here too, but it's when do I divide by 0, right? Okay, so I can solve this one pretty quick actually. This one will also be pretty quick if I multiply both sides by that denominator. Okay, and I'll end up with just x squared plus 2 equals 0. Now this one had such little work. Well, when will x plus 1 equal 0, right? X equals negative 1. And if I keep solving over here, the idea would be to factor that, and then we can set each individual factor equal to 0, and that will give me two more critical numbers at x equals 0 and x equals negative 2. And of course we have the third one, x equals negative 1. Most students, they remember to set the derivative equal to 0, but sometimes people forget to consider when the derivative does not exist. And now we've seen two cases where we had answers on the does not exist. So don't forget that one. Oh my gosh, don't forget to think about when the denominator equals 0. Okay, there are two criticals. These solved pretty well. Didn't encounter too much trouble solving those. So where do we go from there? If you recall, we need to then consider the domain of our function. If you think about the original function, actually here the domain is not everything. At negative 1, we've got a vertical asymptote, so we need to skip negative 1. So there we have it, negative infinity to negative 1, union negative 1 to infinity. Now, since it's just the one value we're skipping, when we draw our domain line, we should take note of negative 1. Now, it happened to turn out that negative 1 was also one of our critical numbers. So even if we had missed that, we would still end up plotting that number. Okay, and we also had -2 as one of our criticals, and 0, and then the -1 was where the derivative did not exist. That makes sense. There's a vertical asymptote there. So it turns out with that vertical asymptote, you might not even catch that. We're going to end up plotting it anyway because the derivative won't exist. Okay, we can see what we've got 4 intervals here, so we need to test each one. Now we're going to pick numbers for each of the 4 intervals, a representative, if you will, and we're going to plug it into, do you remember which function we plug each of these 4 numbers that we're going to choose? Where do we plug it in? To the derivative, because we're testing increasing, decreasing. So I'm going to pick -3. What was that derivative again? That'd be helpful to see. It was x squared plus 2x over x plus 1 squared, right? So for that first interval, let's pick, say, -3. Plug that in. -3 goes in. And I got this. I just kept it as a decimal because I don't care what the number is. All I care about is the fact that it turned out to be positive. Okay, then I'm going to pick something for the second interval. Now here we get something we haven't encountered before. There's no integer between -1 and -2. Well, that's okay. I'll have to pick a decimal value, I guess, in between. I'll pick -1.5. And I can just keep it as a decimal because I don't care what the number is. But it turns out plugging -1.5 into your derivative, it ends up giving you exactly -3, which you don't expect. But of course, we don't care that it's -3, just the fact that it's a negative number. Okay. And if we keep going, we've got to pick a value there. You're like, well, what am I going to pick between 0 and -1? Well, I guess -0.5. Yeah. And it turned out when you plug in -0.5 for your derivative, you get -3 again. And it's, again, that's not unusual to get this kind of symmetry. Of course, we just care that it's a negative number. And finally, something bigger than 0. Let's pick +1. Plug +1 into our derivative. We end up with that positive 0.75 again. So we got a positive there. Positive, negative, negative, positive. Okay, now, of course, the question here was not where is it increasing and decreasing, although we had to find it, but we don't actually have to say it. We can see it right from our domain line. Now, so what I've done, and certainly you don't have to do this in the questions that you do on your own, I went ahead and copied this again just so I can point what is what, and I think I gave it away accidentally. Let's get rid of this. We don't need that anymore. At -2, I can tell that it switches from positive to negative. So is that a local max or is that a local min? Well, at -2, it was going up, then it's going down, so that's a max. It was increasing, then it stopped, and it started going down. Must have been a maximum. Hey, at -1, it did not change. That's interesting. Let's skip that. Let's go on to 0. There it changed from negative to positive. Which type of extrema was that? Well, it was going down, then it stopped going down for a moment, and it started going back up, so that must be a local min. So what's happening? We got a local max, we got a local min. What's happening here at -1? Negative, negative. That's not anything at all. It's not a local max, it's not a local min. If it stays the same, there's a couple different things that could be going on, but in any case, it is not a local extrema, so we don't mention it at all. It was a critical number, but it's not a local extrema. It is possible to be a critical number, but not end up being a local extrema. So, okay, we're ready to finish this off. I can see where my max and min occur, but now all I know is the x values. I would like to know those y values. So I'll take the -2 and the 0, and I'll plug them into the original function to get the y value. Oh my goodness. I just hit it with my side of my hand there. And this will finish the problem plugging -2 in. And you can see, okay, back into the original function was x squared over x plus 1. That gives me -4. So there's a local max at -2, -4. I'll take the 0, plug it back into the original. Well, that just gives me 0. So there's a local min at 0, 0. I highly encourage you guys, go on to Desmos. Where can I write this? Go into Desmos, DESMOS, and graph that original function. See what it looks like and compare your answers. It's kind of a cool looking graph. There's a vertical asymptote at 1, and it's got this curving, and you can see easily that local max and that local min, and you can see the increasing and decreasing. We figured out all that stuff without even knowing the graph. So as your reward, go and graph that in Desmos and just take in that we figured all this out without even knowing that graph. Pretty cool. Well, that does it for 4.1. We're going to continue with this discussion. We're going to go deeper into graphs in 4.2.